All right, in chapter 3, what we're going to talk about is water and the fitness of the environment. And these are the types of things that we were discussing in class when we did the water and methane activity. And the key idea is that water is the medium of life. And so if you look at the planet, this is Earth here, you can see the rock, which is actually the planet. Then you can see that other sphere is all the air in the atmosphere. And then if you look at the water part, you can see that the big, sphere of water there, that's all of the water in the oceans, and then there's two smaller ones kind of in the center there. The bigger of the two smaller ones is all of the fresh water in the lakes, rivers, and streams, and then the smaller of the two small spheres is all of the ice. Okay, so the TOK question that I want you guys to kind of think about and we'll discuss in class, it says that claims about the memory of water have been categorized as pseudoscientific. What are the criteria that can be used to distinguish scientific claims from pseudoscientific claims? So take a little time, think about that, jot some things down, we'll talk about it in class. All right, so we talked about the properties of water. There's four main properties of water that make it an important molecule that allow for life to exist on the planet. We talked about cohesive behavior, water's ability to moderate temperature, the fact that it expands upon freezing, and that water, because of its polarity, is a good solvent. Okay, so some of the attractive forces that we talked about when we were doing our activity dealt with the hydrogen bonds, the dipole interactions, the London dispersion forces, and so forth. And the main thing to kind of keep in mind about the hydrogen bonds is the idea that these things occur when hydrogen bonds to a highly electronegative atom, such as oxygen, nitrogen, and fluorine. Those are the main ones to kind of keep in mind. And then we said that van der Waals interactions, these are the weak intermolecular forces. They have to do with the amount of atoms that you have within the compounds, the molecules, and that there's two different types. We talked about the London forces, of course, and then we talked about the dipole interactions. Okay, so van der Waals forces, these are hydrogen bonds that are very weak individually, but very large, are very strong, excuse me, when they're present in large numbers. So that's what gives water a lot of its characteristics. So when we look at the idea here of this hydrogen bonding and these molecular interactions, they become very strong collectively and give the substances that have them their kind of unique properties, so to speak. And your book talks about an example of a gecko with these van der Waals interactions, these collective forces, along with these hydrogen bonds that we were talking about being very strong collectively and weak individually. While the gecko has these van der Waals interactions between the surfaces of its feet and the table, for instance, that it's walking on the bottom of it. Okay. And then we talked about the idea of hydrogen bonds. Those are creating the surface tension that we see, and allows water striders, for instance, to walk on water. So if you look at this picture here, you can see kind of how the force is spread out along the feet of these things, and then you can almost see how that water looks like it's been bent, and that's due to this hydrogen bonds, these cohesive forces kind of pulling on each other and allowing this bug to stride across the water without sinking into it. Okay, so hydrogen bonds, these are a special type of dipole interaction, and they're a very strong type of dipole interaction, and you see them again containing hydrogen bonded to oxygen, nitrogen, fluorine, those types of things. Water was the example that we used in class, the thing that we spent a lot of time talking about, played with the models and kind of looked at how these things form and due to the electronegativity of those atoms. Okay, so if you look here, you can see the hexagonal type of lattice with the ice, and expands upon freezing, takes up a larger volume, is less dense, and therefore it floats. And then in liquid form, these hydrogen bonds are constantly breaking and reforming and allowing these things to become more dense, whereas with the ice example, it's lost enough energy where these molecules kind of get locked into place, and then as they do so, their density changes and it floats. And that's why solid water is less dense than liquid water, and we discussed this in class as well. Okay, now as far as the dispersion forces go, these are very weak forces, but they generally increase as the number of electrons increases. So if we look at the halogens, group 17, kind of from top to bottom, the number of electrons in chlorine, for instance, the top bulb that you see there, is less than the number in bromine, which is the middle bulb. And you can see now the top bulb is a gas, and then the middle bulb has some liquid and some gas. And then at the bottom you see iodine, and that's a solid, and that's because it's got so many more electrons. So you can see these dispersion forces become greater as the number of electrons increases, and that kind of contributes to the behavior of the atoms, through which these dispersion forces act. All right. Now the dipole interactions, these are a little stronger than the dispersion forces, and these are the result of interactions between the polar molecules. For instance, with HCl, this is a polar molecule, and it's attracted to other HCl molecules. And the idea is that these polar bonds can form, for instance, when hydrogen is bonding to an electronegative atom, and chlorine, of course, is electronegative, and so it sets up this positive pole and its negative pole. And so you get these dipoles, or two poles, as we said, and they kind of interact with one another. Whereas the positive hydrogen is going to interact with the negative chlorine of another atom, and that's going to give it the the dipole interaction, of course, and kind of give the substances the specific types of properties that they have. Okay, and if you look at water here, this is one that we talked about. Oxygen, of course, being negative, pulling these electrons toward it. The hydrogen's positive because it's losing the electrons the majority of time to the oxygen atom. Okay, so then we discussed the thermal properties of water and methane, and this is what we kind of did the activity on. And you can see here, water has that bent kind of configuration because of the unbonded electrons kind of repelling each other, as we spoke about. And then with methane, they're kind of shared equally, so it kind of takes on this tetrahedral form. There's no polarity to it. It's a non-polar molecule. Okay, so now with cohesion, what this basically is these hydrogen bondings working together within the substance, kind of leading to this idea of surface tension. We talked about the cohesive forces. This is between like molecules, okay? And then the idea of surface tension, when you see this water bug walking, you can see these water molecules essentially kind of pulling on one another due to these hydrogen bonds. We talked about the idea of the waxed car, where the beads of water are going to form these beads and then just run off because the wax is nonpolar and it's a thin sheen on the surface of the car, so it allows that water to kind of cling together and then roll off. And then the hydrogen bonds are kind of what are pulling the water molecules in to kind of give it that spherical shape. Okay. Excuse me. Now with the moderation of temperature, some of the things that we discussed was the idea of specific heat, and the heat capacity of water being very high, 4.184 joules per gram degrees Celsius. In other words, it takes 4.1 joules of energy to raise 1 milliliter of water 1 degree Celsius. Okay, so that's quite a bit of energy, and that's due to all of this hydrogen bonding that's going on. In order to kind of change the temperature, or in order to break some of the bonds, that's going to lead to this change in temperature. To get it to go from, say, a solid to a liquid, then a liquid to a gas, it takes a lot of energy because there's so much bonding between these hydrogen molecules, and it has the ability to absorb lots and lots of energy, take on the energy, before it changes the temperature of it. And same thing when it cools down, has the ability to lose a lot of energy and cools down, therefore, very slowly as it's releasing this heat. Okay, so adding the heat to the water does little more really than disrupt these hydrogen bonds. And then once these things start to get disrupted, that's when you're starting to see the change in temperature. Okay, and the water molecules then begin to move faster, and that's when the change in the kinetic energy, for instance, of the substance, the average kinetic energy measurement is a measure of the temperature. So to raise up the temperature of water, again, we have to add lots and lots of energy to it, and then for water to cool down, it's got to give off a lot of energy. Okay, so these characteristics of water really allow it to moderate the air temperatures in regions around bodies of water, because a large amount of heat can be absorbed by the water with little change in temperature, and then that kind of creates that stable kind of climate in and around the area of water. So for instance, on a warm summer night near the lake, it's always just a little bit warmer, for instance, if the water is really warm. And then inland, the land kind of cools down more quickly than the water does, so it might be a little warmer near the lake in the summertime, and then cooler near the inland region, and then vice versa. But the main idea is to take away is that water can heat up and cool down very slowly. So, for instance, it moderates kind of the general climate, through long periods of time. Um, so it might not be quite as cold in Michigan around the lakes as it is, say, in the Great Plains where there is no water that's really moderating the temperature. So it gets very, very cold out there. And, of course, sometimes it gets really cold here, but in general, the lakes moderate the temperature here in the Great Lakes region. Okay, and then you see this all over the world in the Mediterranean region, kind of coastal regions of the United States, and so forth. There's in and around this water, there's lots of moderation of the temperature. Okay. One of the other things now that we talked about was the expansion upon freezing. So water, very unique substance in that when it loses energy, the water molecules kind of get locked into place, and when they do so, what this does is it enables the water really to take on this kind of lattice form, honeycomb shape configuration, and become less dense. And because of that, it expands upon freezing, becomes less dense and floats due to these hydrogen bonds, and then you get these kind of small pockets locked within this lattice region that allows the ice, to float in the liquid. Okay. And then when it freezes from the top down, and we talked about some of the reasons, and we'll go over them in class as well. But from the top down, what it does is it freezes and it kind of insulates that water, so it allows the lake really to not freeze solid. And that's what's going to allow life to exist. Is if it froze from the bottom up, for instance, it being that the water has such a high specific heat, it would never thaw in the summer because it would take too long to thaw out, and it would just be continually frozen solid. So due to this unique kind of property of water, because of the fact that it expands upon freezing and ice floats, what that does is it enables the life to exist below the ice, when it's really cold outside. All right. So you can see here, this is just kind of the same types of things that we've talked about earlier with the hydrogen bonds locking into place, giving the lattice structure, the honeycomb, the less dense on the left there where it says ice, compared to the liquid water where they're kind of packed in more. And then, of course, on the top right there, you can see the gas, they're very far apart. Okay. Now, we also talked about water being a very versatile solvent, and what it does is it allows it to dissolve many things due to the polarity. So the positive regions of the water molecule are going to interact with the negative regions of some of these molecules, and the negative region of water is going to interact with some of the positive regions of certain substances, and that's what's going to allow it to dissolve. For instance, if you look at salt, salt is sodium chloride. You can see it's got positive ions and negative ions, and the positive region of the positive region of the water molecule, the hydrogens, those are going to interact with the chlorines and kind of break those free from the solid salt. And the negative oxygens are going to interact with the positive sodium, kind of pull them apart. So that's what's going to allow ionic types of substances to dissolve in water. Okay, potassium chloride, magnesium chloride, sodium chloride, a whole bunch of these ionic compounds are going to dissolve. Hydrophobic substances now have, no polarity. They're not polar at all, so they're not going to mix with water. They're going to kind of be repelled. So if you think of like salad dressing, oils, vinegar and oil, things like that, they separate out because they're a mixture of polar and non-polar substances. Okay, so hydrophobic means that you're fearing water. Hydrophilic means that you're loving water. So these hydrophobic substances aren't going to interact with or dissolve in water. Okay, so the hydrophilic ones now, salt water or salt, vinegar, sugar, things like that. These are substances that have charged regions on them, and they're going to easily dissolve in water due to the polarity of water. Okay. Now, the last thing we're going to discuss here are the idea of buffers and what buffers do, and we're going to come back to these. This is just kind of an introduction, and certainly if you have questions, you can ask in class, but buffers minimize swings in pH. Large swings in pH. So when you have a lot of hydrogen ions, you're going to be very acidic. When you have high concentration of hydroxides, you're going to be very basic. And what the buffers do is they kind of minimize the swing in the pH. They just try to keep it stable. And a common buffer in the human body is carbonic acid. So if you look at the equation at the bottom, your tissues are always producing water and carbon dioxide as a result of cellular respiration. And we have to get that carbon dioxide out of our cells. So there's an enzyme called carbonic anhydrase, which is going to convert it to carbonic acid, the H2CO3 there at the bottom. And that H2CO3 is very quickly going to dissolve. It's a weak acid into hydrogen carbonate and the hydrogen ion. So you can see that it becomes very acidic. And so what we're going to do is transport this quickly to the lungs, where carbonic anhydrase is going to convert it back into CO2 and water so that we can exhale it out. Okay? So the pH in our blood normally is between 7.35 and 7.45, and if it gets out of that range, it's very harmful to the body. You'd probably die. So what the body does to maintain that pH is takes advantage of this carbonic acid, carbonic anhydrase. And so, in other words, when we're running around very rapidly, exercising vigorously, performing all of the different types of things that we do, where we start sweating, we start breathing hard, and so forth. The reason this happens is because we're producing a lot of CO2. And what happens when that CO2 dissolves in our blood is it produces carbonic acid, so it's lowering the pH of our blood, which is, got dangerous consequences to it. So as a result of this, what's going on is we begin to breathe more quickly and our heart begins to pump because we're trying to get this CO2 unloaded from our lungs so we can get it out of our body so that we can maintain the pH. So in other words, if you were placed into an environment that had a high CO2 concentration, you'd start breathing fast, rapidly, not because so much that you're lacking the oxygen, but because your body is trying to adjust the pH and get rid of this CO2. So what Le Chatelier's principle says really is that we're going to shift the reaction to reduce the stress. So in other words, if you look at the equation at the bottom, if our cells are producing a lot of carbon dioxide and water, that's a stress on the system. So in other words, to reduce this stress, we're going to move this to the right, which is going to produce the HCO3 and the hydrogen ion. And so if we want to get rid of that, for instance, because it's lowering our pH, when we get to the lungs, we're going to move it in the other direction to kind of counteract that stress. So now the stress on the system becomes this acid. So what we're going to do is we're going to run it back through to the carbonic acid. Carbonic anhydrase is going to produce the CO2 and water, and then that's what we're going to exhale from our lungs. Okay? And I'll be going over this certainly with you in class more too when we finish up our discussion and explain it. So certainly if you have questions, please make sure that you're writing them down and you ask them in class, but I'm definitely going to go over Le Chatelier's principle, the idea of these buffers with carbonic acid, carbonic anhydrase, and those types of things. Okay? So if you look here, this is kind of just what I had gone through with you in terms of shifting the reaction right and left and just kind of explaining that to you. And again, you're going to want to make sure that you understand that. And if you don't, we'll get these questions answered. Okay? So that wraps everything up, and we'll see you in class.